All right. Hi, everybody. Thank you for coming. I know there's a few more people streaming in, but it's the last presentation before lunch, so I know you're eager to get this over with and get some food. So we're going to be talking about time-oriented event search, a new level of scale. It's a slightly different talk than what's in the program, or title than what's in the program, but it's the same talk, I assure you. So by way of introduction, I'm Joey Echevarria. I'm the platform technical lead at Rocana. Michael Peterson will be co-presenting with me. He's one of our platform engineers. And I'll talk a little bit about what Rocana does, why we needed our own search engine, and how we sort of architected and built it. So for some context on Rocana, we built an application for handling very large volumes of machine data. What I mean by machine data is think logs and metrics. If you're used to IT monitoring software, we're basically ITOA or ITOM software. Our solution is on-prem or in the cloud. The key thing is we don't do software as a service. That means that each one of our customers installs a version of our application on their own Hadoop environment. This isn't something where we get to manage everything and control everything. That means that supportability is a very big deal for us. We want our customers to have predictability above anything else. It has to deal with wonky environments. We want relatively consistent performance, even if it's not optimal performance, such that there's very little deviation. We also want to make it very easy to configure and operate. And basically, all of our decisions for how we approach event search are informed by these constraints. Your particular environment, your particular use cases may have nothing to do with how we need to use search. And so that doesn't mean you should take everything that we say as gospel. So I said a new level of scale. What do we mean by scale? A typical environment for our customers is collecting tens of terabytes per day. We're talking about every piece of log data generated in their entire data center. This isn't just one department. This isn't just one part of the organization. This is the entire IT staff sending all of their log data. So if you're looking at 20 terabytes of event data per day, and you're looking at event sizes of between 200 and 500 bytes, you're talking between 43 billion and 100 billion events per day that we want to ingest and make available for query. The other constraint that we have is that we want this data to be available online for query for potentially years. That means that we have to make design decisions that allow you to access older data without the existence of that older data impacting the performance of queries on new data. Because the reality is that most of the queries coming in are going to be on that hot data, but you still want to be able to go back without having to do things like replay data by hand or move data around between cold stores and warm stores and hot stores and things like that. So before I get started on our stuff, I want to talk a little bit about what we used before we built our own thing, which is we originally started with Solar Cloud. Most of what I'm going to talk about also applies to Elasticsearch, but Solar Cloud was the system that we were using. And basically, when we started building our application, we wanted to take advantage of a general purpose search system that had high scalability, that could sit on top of HDFS, that could replicate data for us. And Solar Cloud was a very good system for that. It's an amazing feature set, especially for a general purpose search engine. It's got very good support for relatively moderate scale. It's excellent at content search. Think news sites, documents. Really good if you've got a finite data set. So if you've got like a product catalog or something where you may be getting updates, but you're not really getting tons of new data every single day. And then what we call lower cardinality data sets. And when I talk about cardinality, I talk about it in the sense of unique values per field or per column. And so for product catalogs, there's actually a relatively limited number of unique values for every sort of field. Like other than the ISBN number, everything is pretty common between things that are in the same category. The other thing is that most of these general purpose search engines, you talk to the people that have used them at very high scale and very high rates, their data sets fit in memory. Usually it's across a cluster. That's why they're using Solar Cloud or using Elasticsearch. But they're still talking about data sets that can reside in RAM. When you're pulling in 20 terabytes of data per day and you want to have years of that available online for query, you can't store that all in RAM. You have to go to disk. So some of the problems that we found with Solar Cloud, the fixed shard model was very painful. Basically, when you create a collection, you can tell it how many shards it has. That's it. You can't do online changes to the number of shards very easily without sort of re-indexing all of your data. You can do multi-level or semantic partitioning. So by default, they partition by the hash of the event or document ID. You can do things like range-based partitioning based on time by layering it on top, but it gets layered on top. It's not something that you can get down at the storage layer. All the shards are open all the time. That means that even if you have cold data mixed with hot data, you're spending resources to keep those searchers up and ready to go. Which means that the longer that you keep data, the sort of slower everything gets. So one of the things that we found was for customers with very high rates of event ingest, we had to prune their data sets roughly every 5 days in order to keep the performance level consistent. The APIs are more optimized for record at a time and near real-time indexing. There is some support in the APIs for batch-based indexing, but everything also goes over REST. If you take binary data, blow it up into XML, send it over HTTP, and then turn it back into binary data on the other end, you're talking about a bunch of data conversion and a lot of overhead just to do your ingest. Ingest concurrency is wonky. What I mean by wonky is we were only ever able to light up about 2 cores on an 8-core or 16-core system with Solar Cloud. We did as much tuning as we could. And basically, we got to the point where there are all these little things that add up. A big thing is write amplification. The way that all of these systems work is new data comes in, it gets written to disk, it eventually gets merged with older data so that to optimize the index and things like that. With Solar, because you're always writing both old data, very old data and new data into the same shards, that old data gets rewritten many hundreds or thousands of times. And then a bunch of other sort of weird small things. Usually at this point, people ask me a bunch of questions about, did you try this, did you try that? We tried a bunch of different things to scale Solar more, using multiple collections as partitions and doing sort of query planning above the Solar level. That's kind of crazy. We didn't actually get that far, but we did use I don't remember exactly what Solar calls it, but the ability to sort of route events to partitions based on different criteria, and we use time. Because we're a time-oriented event system, every query has time in it. Running multiple JVMs per node, don't ever do that. If you're running it as a service in your own data center and you're the only one that cares about it, that may be fine. But telling customers, yeah, to spin up these different JVMs and configure them with different port numbers and just remember which port is for which process, just don't do that. Pushing historical searches into another system, this is very common where you maybe have like a long-term grep system based on Spark or MapReduce. That's just silly. You want all of your data searchable through one system. Building your own caching layer, again, you really are in a bad way if you have to do that. So at some point, sort of trying all of these different hacks and trying to push Solar as far as we could, we got to the point where building something new ourselves was more expensive than trying to patch over what we had. Again, this is not to say that Solar Cloud or Elasticsearch are not great systems. They are. It all depends on your use case. And for our use case, they just weren't cutting it. Unless you're getting to our scales or getting to use cases that have similar pain points, go ahead and use those general purpose systems. They're going to do just fine for you. Now I'm going to invite Michael up to talk about the architecture of what we built and how we sort of solved some of these problems.
All right, so we built a thing, which right now we call Rocana Search. And I'm gonna, let's dive into the goals and the design of Rocana Search. So here we identified 4 important goals for Rocana Search. And the first 3 are really about scaling better horizontally, scaling better vertically, and scaling better over time. Because remember, we deal with time-oriented data. So everything's coming in with a timestamp, and we can leverage that to build a more scalable system. So we want to do higher indexing per node than Solar, than the product we currently have. We want to be able to scale horizontally better. Hadoop, basically Hadoop limits only. And be able to, as Joey said, have arbitrary amounts of data on disk and not have that slow down current ingest or query of any particular time slices. And the fourth bullet is basically the ability to add and remove nodes without any manual intervention. So as we've said, we run on Hadoop. And so we leverage the features that Hadoop gives us. We write our Lucene, so we built on top of Lucene. We write our Lucene indexes to HDFS. That gives us both our failover model as well as our replication model. And we also do our ingest from Kafka. Kafka is the basic messaging system we use in Rocana Ops from the beginning, and we leverage that as our high throughput ingest feature here. So every node runs an ingester, pulls from Kafka, writes Lucene indexes on to HDFS. There are, within Rocana Search, 4 high-level subservices. There's the indexer subservice, there's what we call the coordinator and the executor, and finally a metadata subservice, which I'll talk about on the next slide. When a query comes in, because we have a sharding model, now we're running on Hadoop multiple nodes. Each individual search of each individual Lucene index, of which there might be thousands, is going to be done by an executor. So that will issue a query against one particular Lucene directory. And again, you might be searching hundreds of them. So a query comes into a coordinator. The coordinator says which partitions are in scope for this query, and then figures out which executors to send the query to. The executors do the actual query, send the fragment data back to the coordinator. The coordinator aggregates, assembles that, and sends it back to the client. So every node is running both of these services, and the query client can contact any node that it wants to do the coordination, and then all of them are running executors. So here in the gold box, you see the 4 subservices I mentioned: the indexing service, the metadata service, and the coordinator, and the executor. And in the purple boxes, you see the 3 external dependencies we have. We leverage HDFS, Kafka, and for metadata, we also use Zookeeper. So if we start with the indexer again, the indexer, as I said, is writing Lucene indexes to HDFS, which is pulling out the data out of Kafka, and the Kafka system is being populated by our data producers, such as syslog type data. When a query comes in, it goes to the coordinator, then to the executors, and then the executor, as I said, is actually what's reading the Lucene indexes using Lucene's query-based system. And finally, the metadata system has an important job of keeping all the nodes in sync. So there's a couple of pieces of information that need to be kept in sync across the cluster. One obvious one is which nodes are actually up and running, because as we said, we want a dynamic system where you can stop and start nodes. The second is around ownership of shards, and I'll talk more about why ownership of shards is important in a few slides. And the third is, because we have a dynamic partitioning model, which I'll also describe in a minute, which partitions exist on the cluster is not known a priori as it is with Solr or Elasticsearch. So as new partitions, new shards are being created, the metadata system needs to keep all nodes up to date on what partitions are on the cluster, which is particularly important for search to know which directories to search. So let's talk about our sharding model. We don't actually use the term shard. I've used that term so far because it's a more generic term, but we talk in terms of time partitions and slices, and also data set. So data set is our generic term for basically any ingest schema. Right now we only support one ingest schema, which is the basic one we use for our ingest, like our syslog type data. In the future, we will expand to support multiple data sets. We take each data set and then time partition it into using a partition strategy. Right now we support 2 of them: year, month, day, or year, month, day, hour. So each event that comes in has a timestamp, and that will route it to a particular directory, basically on HDFS. So our partition strategy model is very similar to the Kite or Hive partitioning model, where it's basically directory-based in HDFS. And then that partitioning model is invisible to queries. You just say, again, all of our queries have this format of from time X to time Y, and potentially some additional things like host equals foo. We can then figure out which time partitions we actually need to search without having to search everything. So the time partitioning model is the first part of our sharding model. The second part of our sharding model is we then divide these partitions into what we call slices. So for a particular day, we might have, in this example, 20 slices. That's 20 separate directories where 20 separate Lucene indexes are getting written. So the slice is the lowest level. Each of those is a Lucene directory. And we also tie the number of slices of each time partition to the Kafka partitions. So Kafka, when you set up a topic, you can define the number of Kafka partitions that it will have. If you set it up as 20, then we're going to be ingesting in parallel 20 separate streams. That means we're also going to be writing to 20 separate slices for each time partition. So let's look at this graphically and have that make a little sense, because the term partition here is overloaded. There's both Kafka partitions and our time partitions. So I'll try to use those two terms to make it clear. So for a particular data set, in this example, we have two time partitions, January 1st and January 2nd. And we defined n number of slices, which is again determined by the number of Kafka partitions that you set up when you created your Kafka topic. So every partition, time partition, will have the same number of slices. And then as events come in, you route them to the right time partition and slice. So here is a 3-event model. Events 1 and 2 are for January 1st. Event 3 is for January 2nd. Those come into Kafka. They get routed through a hash modding system where we basically look at the body of the event, figure out which Kafka partition it needs to go to. So in this case, event 1 went to Kafka partition 0, and events 2 and 3 went to Kafka partition 1. When the Rocana search pulls them out of Kafka now, it's pulling them out at the level of the Kafka partition. Event 1 is going to go to slice 0 because it came from Kafka partition 0. But its timestamp, when we look at the timestamp, we hand it the partition strategy and say, which directory does this go to, which time partition? And that's for January 1st. Events 2 and 3 came from Kafka partition 1, so they will go to slice 1, but they have different timestamp periods. One goes to January 1st, one goes to January 2nd. So I mentioned a little earlier the idea about ownership of a shard. And the idea here is that if you look at the 2 purple nodes, those are 2 separate Rocana search nodes, each of which has 4 time partitions. So events have come in mapping to 4 different days so far. And there's 4 slices because we set up Kafka with 4 topics. Or sorry, the Kafka topic with 4 partitions. In this case, each time slice is going to have 4 slices. Sorry, each time partition is going to have 4 slices. But an individual node will only have a subset of those as defined by Kafka. So when a Kafka consumer registers with Kafka, it looks across its set of consumers and says, well, here I have 4 Kafka partitions and 2 nodes. So I'm going to give two Kafka partitions to this one and the other 2 to that one. So in this case, Kafka made the assignment of slices 0 and 2 to node 1 and 1 and 3 to node 2. But that's dynamic. If node 2 was to go down, Kafka should rebalance and give all the slices over to node 1. Or if we added a 3rd node, Kafka would rebalance and give 2, 1, and 1 to the 3 new nodes. So that's one way we can, that's the heart of why we can add and subtract nodes dynamically. So let's talk more about the write path. Each search node at any given point in time owns a slice. And a slice is only ever owned by one node at a point in time, but that ownership can change over time, as I mentioned a second ago. We also consume in batches for throughput, so we pull off Kafka in batches and then write to Lucene in batches. As each event comes in, we look at its timestamp. We use the partition strategy to figure out what time partition it needs to go to. And then we can ask the Kafka message that came in, which Kafka partition did you come from? And then you know which slice to write it to. With the time partition and the slice data, you know exactly which directory on HDFS to write it to. And then we have a configurable model for how often to commit, to do Lucene commits. So you can set it to 1 minute, 5 minutes, 10 minutes, whatever makes sense for your throughput needs. And then finally, because we have a time scale model, a scaling model, where as each new day arrives, we are going to create new partitions. What exact partitions exist on the cluster, like when did you start and how far have you gotten, is not known a priori. So the metadata service is basically in charge of keeping the system up to date. And as new partitions are created by the indexers, they inform the metadata service, which then broadcasts that out. So the slice ownership is very important for the query side. So queries come in via RPC. We use Avro for both our data storage format in Kafka and also for our RPC model across the cluster. When that query comes in, the coordinator hands it off to Lucene and says, parse this query for us. That gives us back an AST. We can walk the AST to basically figure out which time partitions are in scope and only search that subset as opposed to everything that's on the cluster. So with this pruning model, we can basically be resistant to however much data you have and only focus on the areas we need to query. Once the coordinator knows which time partitions to search, then it's got to send it to all the slices. And each executor, it'll send it to one executor per slice. And you want to send it to the executor that owns the slice. So ownership means, as I showed on the diagram before, Kafka has assigned slice 0 to node 1, say. Node 1 is actively writing to that slice, or may have actively written to it yesterday if it's been up for a few days. So by sending the query to the executor that's on that same node, you get a couple of advantages, which is you can basically do, you can leverage local writes. You can also leverage Lucene NRT, near real-time index features, which basically can search the RAM that's been written to that hasn't yet been committed. So the coordinator looks up in the metadata system and says who owns each slice, sends the executor to that slice. And as I said before, that's then queried, sent back to the coordinator, and that assemblage is sent back to the client. So some benefits of this design. As I said a minute ago, the search processes and the search ingest, the searching and the ingest are happening on the same node, and we preferentially send the queries to the nodes that have the ownership, which means we're getting the advantage of local disk reads and also possibly local RAM reads if it's currently being actively indexed by Lucene. So that gives us HDFS short circuit reads, and we could actually leverage additional HDFS caching features, which we're not yet doing. For search, we also use off-heap block cache, basically the same way that Solr does. And then I talked about our failover model. If any node goes down, any other node can take over those slices. And even if a node doesn't go down, for some temporary reason, nobody owns this slice in Zookeeper, which is where we keep the slice ownership information. The coordinator can look and say, well, nobody currently owns slice 3. It doesn't give up and say, well, I can still send that query out. I can pick any node to look at slice 3 because with HDFS, basically you can just do across network reads as a failover model for queries. So there obviously is always HDFS overhead, but that overhead gives us our replication model, and we can actually minimize the overhead in terms of writes and in terms of queries because we try to always go to where it's local. So this product is not yet GA. We're still building it, so I have done some initial benchmarks. I figured you'd want to see where we're at on that. But this is still early days. This is all preliminary and subject to change. But on the most recent head-to-head we've done of Rocana search versus Solr, using these conditions, CMS garbage collector, both running on HDFS on this AWS setup, running a small cluster, just 4 nodes and 8 shards. We did a 12-hour run, which in that 12 hours, Solr indexed about 300 gigabytes with events that are about 400 bytes each. And Rocana search actually ended up indexing almost a terabyte in that same time frame. But at the comparison point, at 300 gigabytes on disk, these were the numbers we had gotten. Solr was doing about 11,000 events per second. Again, these are about 400 byte events. Rocana search was doing over 36,000. So from these initial numbers, we're happy to see Rocana search looks to be about 3x faster per node against Solr. And we actually expect it will do better longer over time. So if you do a 5-day run or a 2-week run, Solr, as Joey said, is going to have to keep writing to its same shards over time. Whereas Rocana search will evolve new shards over time, so you have smaller indexes to search and write to every day. So we hope to see these numbers even better when we do the longer runs. The last set of benchmarks I have are around query, and I have 2 here. The first is a query round trip during ingest. So that means while all the nodes are actively ingesting a large data stream as fast as they can. And so this is a latency distribution by using percentiles. On the y-axis, basically, it's seconds. So this says Solr is the red line, Rocana search is the blue line. So during ingest, 90% of Solr queries were done in about 1.5 seconds, and Rocana search is about 2 seconds. So we are slower than Solar, and in fact, here's a similar graph for a case with no ingest. Currently, we are slower than Solar. Our goal is to at least be competitive. We have a number of optimizations we know we can apply to our query model, which we haven't yet gotten to. So we hope these numbers will be better in the near future. So to sum up, have we achieved our goal? What have we shown? We believe it is possible to build a search engine that's based on time-oriented data, built on a time partitioning model that can deal with the high cardinality data sets we're going to get, do the high-speed ingest of terabytes a day, not having to age anything out of the data set, handling both ingest and concurrent queries at the same time, and fully utilize modern hardware. Maximize the CPU. We have a threading model where we can basically peg the CPUs during ingest, leverage the network, and leverage local disk reads on HDFS. So we believe these things are possible, and have been happy with our results so far. So with that, this is the Rocana search team that's worked on this, and we'll take questions now.
So the question was, we're using Avro encoding for the events in Kafka, and do we only support one schema? Do we have multiple schemas? Right now, we only support one schema. Our application is built with a generic event schema that we use for everything in our system. That being said, we do have plans for Rocana Search in particular to support multiple schemas in the future. We just haven't figured out all of the details for how we want to do that, as well as where we want to store the extra schema information about the sort of Lucene side of things.
Do you have an idea about the overhead of using Avro serializing?
So the question was, do we know an idea of what the overhead of using Avro for serialization, deserialization is? We do have some numbers on that. It's very small. The deserializing is way less than 1% of one core from a CPU perspective, and it's mostly CPU that you would worry about there. The nice thing is that Avro does compress fairly well. So if you turn on Kafka compression, you can get the over the wire size down pretty low. So yeah, we don't have a big overhead from Avro serialization or deserialization. Our biggest bottleneck on ingest tends to be CPU utilization by the Lucene indexers themselves.
I had done benchmarking at my previous company of JSON parsing versus, say, Avro parsing, and Avro parsing was many times faster, like 10 to 20 times. So. Back.
Do you have any security about, for example, integration with Kerberos?
I think the question was about security and integration with Kerberos. That's a great question. So we both have integration with Kerberos on the HDFS side. So if you have an HDFS cluster that has Kerberos enabled, we will use Kerberos authentication for writing the Lucene indexes and talking to HDFS. We also have Kerberos-based authentication for RPC clients. So if you're talking to us with a search client, you can enable SASL-based RPC over that interface. And then lastly, the one place where we don't currently have support for Kerberos is in Kafka itself. So we build against Kafka 0.8.2, which is before Kafka had security features. We do hope to be able to upgrade to Kafka 0.9, but as we said at the very beginning, we build an application that we have to ship to customers, and so we can't always move to the latest version of things. We have to work with environments that will meet the needs of the customers. So we do hope to be able to move to Kafka 9 and be able to support the Kafka features on security features on ingest, but that'll be pending an update to our libraries.
Yeah, many of our customers are enterprise customers, and they require Kerberos integration. So we've built that in from the start. What we haven't done yet is benchmarks, so we don't know how much that's going to affect query and throughput.
Yeah, we do expect that having Kerberos authentication will lower at least query performance, because that's the main place where it'll be in our system, but we haven't benchmarked it yet.
Have you thought about anything
anything to reduce the storage needs, let's say for the very cold data. So if you pile this up, I learned yesterday is that there's something going on with HDFS where we can have very cold data on some of the 3 nodes and very hot data on more.
Yeah, that's a great question. So to repeat the question for everyone, have we thought about ways that colder data can reduce the storage footprint versus hot data? And we have thought about it. One thing that we do differently than Solar, although Solar has some support for this now, is from the beginning, we've always relied on just HDFS for replication. Solar actually has 2 different levels of replication. It'll replicate on the HDFS layer for the indexes themselves, and then you can turn on replicas above that. And in fact, with Solar, the only way to get read replicas is to replicate at the Solar level. That means that now if you have one event coming in and you have 2x replication, you're actually writing 6 copies onto disk, 3 times on HDFS twice. We don't do that. If we have read replicas, like Michael said, if the primary node hosting a particular index is down, we will just route it to another node and it'll just open up the files off HDFS. So that's one thing. We have also, and so one of the things that we've thought about is in the future, we may want to warm up some of those read replicas, which means that instead of just sort of picking a node and having to read it off of disk, we may have some nodes sort of primed for reads so that if you have a very high concurrent query load coming in, you can take advantage of that and actually query multiple nodes in parallel. And one of the things that we've thought about with doing that is we would have more sort of warm read replicas for hot data, for newer data, versus older data, where we would only have sort of one primary replica or read replica. The other thing is HDFS does have some features for sort of controlling the replication factor or using sort of different encoding schemes so that you can sort of get the effective protection of 3x replication with a lower on-disk footprint. We haven't tested with those, but that is something that we could leverage. And that was part of the reason why we built on top of HDFS as our storage model, is we didn't want to have to reinvent all of that. We wanted to be able to take advantage of all of the great innovations happening on the HDFS side.
What kind of front ends integrate natively?
Say that one more time.
What kind of front ends integrate natively?
Do you want to talk about that?
Front ends?
Front ends, like, so I think you mean like languages for query clients and things like that?
Yeah, do you only provide some API for programmers to communicate with it, or do you support some kind of front ends to communicate with this search system?
Gotcha.
Okay. So all ingest right now is through Kafka. So if you push into Kafka, with any language, we can pull it out. It has to be in our schema right now, but again, we're going to adopt a model that can have the multiple schemas in the future. In terms of query, right now we only support Avro query RPC. We may add REST at some point if the use case arises. Would you agree with that?
And then, so our application, Rocana Ops, which is the name of our application, comes with a web interface, which is how customers primarily access our data. And that web application that runs that UI does have a REST endpoint, which you could use to query us via another API. But the 2 ways would be that REST API or the Avro RPC. And we're going to be shipping on day 1 with a Java-based client that's built to speak the Avro RPC.
If I understood well during the presentation, the indexing was based in the date, but the architecture supports other kind of indices. I mean, secondary indices.
Yeah. So the question was, in our architecture diagrams, we focus very heavily on like the partitioning by date and sort of indexing by date. But do you support sort of more flexible partitioning strategies or indexing strategies? And the answer is yes. So our partition strategy that Michael talked about, it supports date-based partitions. It can go down to hourly if you want. Most of our customers do daily. But it also does support hash-based partitions on other fields. So if you have other fields that you know are going to appear in every query, then you can enable hash-based partitioning on those fields, and that'll, again, let you sort of winnow down the data at the storage layer. And in particular, for our event schema, we've got timestamps, host, service, and location, which are strings by default, as well as an attribute map, which is basically just arbitrary key value pairs that we index against.
Do you plan to support any kind of join between series or other data?
So that's a good question. Do we plan to support joins between different data sets or against other data in the future? We haven't thought too much about that. We are focused on sort of the search use case. That being said, one of the things that Rocana does have is this embedded library that we use for data transformation. And one of the things that that supports is the ability to do either data transformation on lookup and eventually on query, where it could be able to sort of join data with sort of like small data sets. So one example there is a lot of data coming in has IP addresses, and you may want to do geolocation on those IP addresses using like the MaxMind database or something like that. So that's something that we support today purely on ingest. In the future, we want to be able to run that transformation library over the results as they're streaming out of the query. I think there was a question over here as well.
It's just about building Elasticsearch.
Yeah.
So you look into that, or that's out of your technology stack in that sense that you are having only on more mature Solar and Elasticsearch is newer.
Gotcha. So the question is, did we evaluate Elasticsearch more thoroughly? And the answer is no, not really. We've read a lot about Elasticsearch, and in particular, we've read, there's a developer, his sort of screen name, his name is Kyle Kinsberry, his screen name goes by Affer, but he's written a Call Me Maybe blog series using a tool called Jepsen to do testing of distributed systems from a sort of correctness perspective, basically throwing a bunch of data at systems, creating a bunch of network partitions and saying like, okay, do you lose data? Do you acknowledge writes that you then later can't serve back? And Elasticsearch has had a few issues there. So based on the power of those results, we sort of discounted Elasticsearch kind of from the beginning. That being said, it's a great tool. If your search index doesn't have to be your data store of record, using Elasticsearch is a great way to add searches to your stuff. Any more questions?
You support any kind of batch processing because you showed streaming data, but I had some initial loss of data I would like to index.
Yeah, so that's a great question. Do we support batch indexing? And the answer is sort of. So Kafka can actually support very, very high throughputs. And so on large clusters, doing sort of like pure batch indexing where you're writing directly to HDFS versus writing to Kafka, based on our benchmarks, there's not a huge difference. So what we're building is a MapReduce job that can read historical data sets. So one of the things that our application does is, in addition to writing everything to the search index, it always writes a full copy of every event to HDFS in what we call sort of our, in case of emergency, break glass data set. And this tool will basically spin up a MapReduce job or possibly a Spark job. We haven't decided which one to use. Read the data in parallel, write it to Kafka in parallel, and basically support high throughput bulk loads through Kafka into our system.
Yeah, we do have that. As we have something called data lifecycle management, which basically can, in our case, it publishes messages into Kafka and says delete data that's older than X. So we have a separate process that do that in the background. That actually exists. We have that for Solar as well. So.
And then one other thing related to that. So the question was about like pruning of data and also like optimizing of older data sets. One thing that I don't think we mentioned during the presentation, but because most of the data is coming in time order, older indexes, we automatically sort of close the index writers for those older indexes just as they sort of time out. One of the things that we could do in the future, but we haven't done, is run sort of a final optimization step to fully optimize those old indexes, because they're not going to be written ever again, which means most likely. There is obviously delayed data, and you may have to like reindex data for some particular reason. But for the most part, older indexes, once they're written, you're done with them. And so that is something that we've thought about for the future, of being able to sort of have a background thread that optimizes old indexes so that the on-disk format is as optimal as we can get it.
Mm-hmm.
All right. Thank you very much.